Today, we're going to talk about the science of change itself, how stuff transforms from a solid to a liquid to a gas. This is what's known as a phase transition. And honestly, it's happening all around you, all the time. Think about an ice cube melting in your drink, or even the clouds forming up in the sky.
Okay, let's start this whole thing off with a bit of a puzzle, something you've definitely seen in your own kitchen. You're trying to cook some pasta, you're in a hurry, so you crank the heat on the stove all the way up. The water boils like crazy, but the thermometer, it doesn't budge. So what's going on there? And here's the second part of our puzzle. If you took that exact same pot of water and tried to boil it on top of a mountain, it would actually boil at a lower temperature. It's the same water, the same pot, so what gives? Stick around and we're gonna unravel both of these little mysteries. To figure this out, we have to zoom way in, all the way down to the molecular level. Let's start with a solid, like an ice cube. Inside that cube, all the water molecules are packed super tight in a rigid structure. They're held together by this kind of molecular glue. Scientists call these intermolecular forces, and in a solid, that glue is incredibly strong. Now, what happens when we start adding energy? Say heat. Well, that molecular glue starts to get a little weaker, and that's when we get a liquid. The molecules can now wiggle and slide right past one another. The forces are still there, for sure, keeping them all together, but they're not locked in place anymore. And that freedom of movement is exactly what lets liquids flow. And if we keep pumping in more and more energy, that's when we get a gas. In something like steam, the molecules have so much energy that they basically shatter that molecular glue completely. They just break free, spreading way far apart and just zipping around all over the place. At this point, those intermolecular forces have been almost totally conquered. So, you see, it really all boils down to the strength of this molecular glue. If those forces are really strong, it's way harder for molecules to break free and escape as a gas. That means it's tougher to melt and tougher to boil. And this resistance to escaping, it creates something called low vapor pressure. But if the forces are weak, molecules can escape super easily, and that leads to a high vapor pressure. Remember that term? We're going to come right back to it. So let's take a closer look at this whole vapor pressure idea. Just imagine you have a sealed bottle of water. Even at room temperature, some of those water molecules have just enough energy to escape the liquid and become a vapor. That's vaporization. But at the exact same time, some of those vapor molecules will bump back into the liquid and get trapped again. That's condensation. Eventually, the rate of escape perfectly matches the rate of return, and that perfect balance is called dynamic equilibrium. And that brings us to what vapor pressure actually is. It's the pressure created by all those gas molecules hanging out above the liquid in that state of equilibrium. So a high vapor pressure means the liquid's molecules are practically jumping out of it. A low vapor pressure means they're much happier to just stay put in the liquid. And you can see this principle in action right here. Just look at these different alcohols. As the molecules get bigger and more complex, going from methanol down to butanol, that molecular glue gets stronger. And what happens to the vapor pressure? Look at that, it drops like a rock. Stronger glue means fewer molecules can escape. It just makes perfect sense when you see it laid out like this. Okay, here we go. This is it. This is the one idea that unlocks our entire puzzle. The real scientific definition of boiling isn't just when a liquid gets hot. No, it is the very specific temperature where a liquid's internal vapor pressure becomes strong enough to equal the pressure of the atmosphere pushing down on it from the outside. And that right there is the answer to our mountain puzzle. When you're at a high elevation, like in Leadville, Colorado, there is literally less air pressing down on you and on your pot of water. The atmospheric pressure is lower, so the water's vapor pressure doesn't have to work as hard to match it. It reaches that boiling point at a much lower temperature, around 90 degrees Celsius. Puzzle 1, solved. But okay, what about our kitchen puzzle? Why does the temperature just get stuck at 100 degrees? Well, that's because once water hits its boiling point, all that extra heat you're pumping in from the stove gets a brand new job. It completely stops making the water molecules move faster, which is what temperature actually measures. Instead, every bit of that energy is now used for one thing: breaking that molecular glue and launching molecules from the liquid into the gas phase. Let's map out this whole journey. You start heating ice, its temperature goes up, but then, boom, it hits the melting point. Notice that first flat line? The temperature just plateaus because all the energy is busy breaking apart that rigid, solid structure. Once it's all liquid, the temperature starts climbing again, until it hits the boiling point, our second plateau. And only after every single last drop has turned to steam can the temperature of that steam start to rise.
So that first plateau for water happens at 0 degrees Celsius. At this exact temperature, you can have both solid ice and liquid water existing at the same time. And all the energy coming in is being used for just one thing, breaking the bonds of those ice crystals. And that second plateau, at sea level anyway, is at 100 degrees Celsius. This is what we call the normal boiling point. And just like with melting, you have liquid and gas coexisting, and that temperature will not budge until every last molecule of water has been turned into steam. And there you have it. Puzzle 2 solved. So what do scientists call all this hidden energy? The energy that gets absorbed during melting without actually changing the temperature. Well, it's got a name, the enthalpy of fusion. It's the precise amount of energy it takes to weaken that molecular glue, just enough to turn a certain amount of a solid into a liquid. And as you might guess, there's a similar term for boiling. The energy you need to turn a liquid into a gas is called the enthalpy of vaporization. This number is usually way, way bigger than for melting. And that makes sense, right? Because you aren't just weakening the molecular glue anymore. You're completely shattering it. Now, while most things follow that familiar solid-liquid-gas path, some substances, well, they like to break the rules. They can skip the liquid phase entirely. When a solid turns directly into a gas, like when dry ice makes that spooky fog effect, we call that sublimation. And the reverse process, a gas turning straight into a solid, like when you see frost forming on a cold window, is called deposition. And just like melting and boiling, making this huge leap requires a specific amount of energy. Scientists call it the enthalpy of sublimation. It's the energy you need to overcome all those intermolecular forces all at once, launching the molecules straight from a solid into a gas. So why does any of this really matter outside of a science class? Well, think about cooling off on a hot day. The sweat on your skin evaporates, right? To do that, it needs energy, that enthalpy of vaporization we talked about. And where does it get that energy? From your body heat. It's literally pulling warmth away from your skin to power its escape into the air. And on a much bigger scale, the entire water cycle of our planet is just a massive engine running on these exact same phase transitions, driving all of our weather and climate. All right, let's just quickly recap the big ideas here. First, phase transitions are all about overcoming that molecular glue, those intermolecular forces. Second, and this is crucial, during a phase change, the temperature gets stuck. It holds constant. Third, boiling isn't just about heat. It's this delicate balance between a liquid's internal vapor pressure and the external atmospheric pressure. And finally, all that hidden energy that powers these changes has a name, enthalpy. And that kind of brings us to a final thought. We've just peeled back the layers on something as simple as a pot of boiling water and found all this deep, complex science hidden inside. It really makes you wonder, doesn't it? What other everyday things have these incredible secrets hiding in plain sight, just waiting for us to get curious and ask the right questions?